Mobile phones often have difficulty capturing clear images of moving subjects, such as a kid jumping around. This is because motion often leads to blurry images. Due to the limited light collection efficiency, this challenge is very common on mobile phone cameras, especially in low light conditions. To address this issue, researchers have proposed a novel work on mobile cameras, face deblurring using dual camera fusion. When face motion is detected, the ultra-wide camera captures a reference shot with a faster shutter speed. The main shot from the wide camera can be blurry. In contrast, the reference shot from the ultra-wide camera is sharp but noisy. This work uses deep CNNs to align and merge these two photos effectively. The result is a sharp and clean face image. This entire process took only half a second, so users can see the enhanced image immediately after the capture. To minimize motion blur, mobile cameras usually reduce exposure times. However, this approach leads to noisy images in low light conditions. In addition, under specific artificial lightings, longer exposure times are necessary. This is to avoid banding caused by rolling shutter effects. Therefore, shorter exposure times cannot always be the solution. Some previous works rely on iterative optimization to estimate blur kernels. However, these methods are too slow and may produce artifacts or unnatural results. Some other approaches use deep CNNs to address blur without estimating blur kernels. Yet, these models need high memory requirements, making it difficult for mobile deployment. Furthermore, they often fail to address unseen images effectively. Reference-based methods like this work use an additional image for deblurring. In other studies, they capture short and long exposure shots in sequence. However, aligning these two shots becomes challenging when the subject moves quickly. So what's the solution? In this work, instead of capturing two shots in sequence, they take the main and reference shot at the same time. It used the wide and ultra-wide cameras for this purpose. In this approach, alignment step only has to manage the parallax caused by camera's baseline. This method is simpler and more likely to produce satisfying results. The system first captures the raw burst from wide and ultra-wide cameras. Then it merges them into linear RAW. Next, it crops the face from both images. It applies deep CNNs to align and fuse faces for deblurring. After fusion, it blends the deblurred face back into the source image. Now it's time for post-processing steps, including tone mapping, to result a clear and sharp final image. Now let's talk about alignment and fusion steps in detail. First, by adjusting the color conversion matrix, they match the colors of the two images. Then they create a face mask by using subject segmentation. They use the PWCnet to compute the optical flow between source and reference image. The optical flow is used to warp the reference image. It also helps estimate an occlusion mask. The fusion net then takes the source image, warp reference image, face mask, and occlusion mask as inputs, and it generates the deblurred face. When using optical flow for alignment, full images led to poor results. This is due to the motion magnitude in the PWCnet training dataset. To solve this, they downsampled the input images to estimate the flow. Then they upscaled the flow. This significantly improved alignment quality. To reduce latency and model size without losing quality, they use an optimized PWCnet, features a mobile net backbone. By focusing on color consistency loss, in addition to content and perceptual loss, they manage the color differences between two camera shots. To address power and thermal issues, an adaptive system is implemented. It activates the ultra-wide camera only as needed. This activation is based on predictive modeling from camera metadata. Quality checks are conducted before and after fusion. This prevents the delivery of the images with noticeable artifacts. Therefore, it guarantees the production of only the high-quality images. Compared to existing methods, this approach excels in speed, quality, and efficiency. Deployed on devices like Google Pixel 6, it shows remarkable effectiveness in real-world conditions and images. And finally, it significantly enhanced the experiences in mobile photography. Thanks for watching.